I've just finished making an RGB mod for the SNES, and customers are already ordering them through our prototypes on Discord. I've come to install them on this SNES for the customer, and there's about 13 revisions of SNES consoles, and this one in particular has some issues on the AV output. So I'm going to show you how we're going to figure out what the problem is, fix it, and then open source the knowledge. So we've got the SNES here, we've got the Edge Buster that cleans up the ghosting, and we've got the clean RGB, which gives us perfect RGB. It's all routed out through the actual back of the console this time. We've got some new wireless and wired Super Gamepad Pluses in now, so I'm going to use these wired on this console for testing. But let me show you the issue. If we turn on, this should be absolutely perfect, and you can see we have a big vertical band through here, and also a ton of what looks like clock noise. So if we just use the new Super Gamepad, we'll navigate to the test suite. And this is where I like to focus on making it nice and sharp. And you can see that really obvious band down here. We'll tackle that after. I don't know what that is yet. But you can see all of this clock noise. See all this diagonal noise here? That's usually a chroma clock. You can see I've sharpened the edges up perfect. We just need to remove this noise. So if we pull up the scope here and probe on, say, the red channel here, you can see on the spectrum we have some peaks here of potential interest and noise. If we zoom in on the first two peaks and drag out a line, drag out because there's harmonics, so these pulses repeat. You want to measure between two peaks to get a potential frequency, and you can see that falls right around the chroma clock frequency. There's also potentially some 10 megahertz or maybe some harmonics in here of maybe 5 megahertz. So let's take a look at the circuit board. The place of interest is the PPU under here that generates these signals, because the red, green and blue signals are the things picking up noise. In order to do that, I've gone ahead and completely stripped another console, fully desoldered it, cleaned it, and scanned this in so we can take a look, or we can just look with our eyes. The red, green and blue are these two vias and this via. And looking at the schematic, you can see we have a 5M out and 5M in, so that's a 5 meg clock, that will definitely be of interest, and another 3.58 meg clock. So these two are very likely going to be the cause of the noise. So we want to find R98 and C69 to find these traces, or just follow pin 27 and pin 3. If we flip over the board and follow all these vias, we'll find that this pin is the blue, this one is green, and this one is red. So this trace running down here is blue, this is green and red running down here, and would you believe the one next to it is the 5 meg clock, and the one next to that is the 3.58 meg clock. So this trace, or these two traces here running alongside these two colours, will 100% be adding noise. What we need to do to fix that is to cut the traces right where they're coming out of the PPU, and then we'll route them past these traces. So that's the traces cut at the start of each, or in this case I've just sideways the resistor so we don't have to cut a trace. This one's been redirected up to R29, where I've also cut the trace coming out here. So let's see what this does. And we still have different noise. We've got the bar down the middle. We've got what now looks like more of a rolling noise than a static sort of chroma grid. So this doesn't look solid. When it's chroma, specifically, it would just be static. And if we look at the spikes and the noise there, and then I grab the controller, if you notice when I move up and down, it's probably hard to see on the picture, but see that noise appearing? So every time I'm tapping the button, see the noise appearing in the grey. And if we look on the scope, when I move left and right or up and down, see how it bounces around? So that is going to be RAM. So let's do a little trick. I've isolated just the green channel. We can see all the noise here very distinctively. And instead of guessing where the noise is, if we just attach an enamel wire and a resistor, so I've got like a 40k resistor here, we can now probe around on anything. So clocks, RAM, CPU, and let me show you an example. So if we probe on, say, if we're suspecting this chip here, the CIC chip, of adding noise, we can just touch in here, and this is the noise of that specific pin. If I let go, it goes back to normal. So we can see with noise removed, it's not exactly the same. This is kind of static, whereas this noise is moving, and distinctively this bar will give us a clue where the noise is. So now if we tap this on, say, the RAM pins, let's just pick a random pin, and as we do that, see, that just basically got exactly the same but brighter. And there you go, look at that. So there's that bar in the middle. Let go. And different RAM pins will give you completely different results. So there's one pin, there's another pin, and once it corrupts, because we are effectively tapping on the RAM, it's going to do things. I'm pretty sure that one right there, with that distinctive middle line, gives away the fact that it's RAM noise. So what we next need to do is look for where all the RAM, so this is where this comes in handy. Now I've stripped everything. We need to check all these RAM traces and where they cross over the RGB traces. It could also be that the RAM simply needs more capacitance, but this has turned into a whole new problem solved now. So we've removed the chroma signal and the 5 MHz signal, but we're left with still what's pretty much stronger than those two signals of interference that we need to solve. Once I figure this out, I'll chuck it on the wiki, but if you're interested in a part 2 maybe of diagnosing the RAM and looking for the output, let me know and I'll do a follow-up video on that.